Hello students, in today's class you are going to learn about heating effects of electric current. We all know that the electrical appliances which we use in our daily life consume electric energy. So the electrical appliances like fan, refrigerator, heat, cooler, cooker, washing machines, all these they consume electrical energy. And when we use any electrical appliance for a longer time, it becomes warm. So here when we are using the electrical appliance for a longer time, means when we keep running the appliances or when we keep using them for a longer time, we can observe that it gets warm. And on the other hand, if the electric circuit is purely resistive, the source energy continually gets dissipated in the form of heat. So here, when we are using the electrical appliances for a longer time, it becomes warm. And on the other hand, if suppose the electrical circuit is purely resistive, then the energy which is supplied by the source gets continually dissipated. Here dissipated means it gets wasted in the form of heat. This is known as heating effect of electric current. So here you have come to know that heating effect of electric current is nothing but the energy, that is the heat energy, which gets dissipated in the usage of electrical appliance is known as heating effect of electric current. We all know that battery is a source of electrical energy. A part of the source energy in maintaining the current may be consumed into useful work and the rest of it is expended in heat to raise the temperature of the appliance or gadget. So here it means that a battery, which is a source of electrical energy, will supply the electrical energy and some of the energy is used to maintain the current in the circuit for useful work, whereas the rest of the current, that is the rest of the electrical energy, is spent to produce heat to raise the temperature of the appliance or the gadget. So here the generation of heat is an inevitable consequence of electric current, which means that when electrical energy is supplied in the circuit, some amount of electrical energy is used for useful work and some of it is converted into heat, and this conversion of the heat, that is the generation of heat or the production of the heat or the release of the heat, is an inevitable consequence of electric current. So here when electrical energy which is produced by the battery is used by the appliance or the electrical gadget. So here when some amount of energy is used, as a result of this usage of electrical energy, it also produces heat. So this generation of heat is the consequence which is inevitable, means which cannot be stopped, which cannot be avoided. So the generation of heat is an inevitable consequence of electric current. However, heating effect of electric current has many useful applications like laundry iron, electric toaster, oven, kettle, electric heater are some devices based on Joule's law of heating. So these are the some appliances which work on the law of Joule's, which is known as Joule's law of heating. Heating effects of electric current. So the amount of heat which is produced, that is dissipated during the process, is converted in a useful manner so that it is applicable and useful for us in other way. Now when an electric current flows through a wire, the wire heats up. Electrical energy has been converted into heat energy. So here when an electric current is flowing through a wire, this you must have observed also, the wire gets heated up. How it is getting done is, here the electrical energy is being converted into heat energy, and the greater the resistance of the wire, the greater is the amount of heat produced. So it means that the amount of heat produced in a circuit will be greater depending on the resistance of the wire. If the resistance is greater, then the amount of heat produced also is greater. This heating effect is used in common electrical appliances like which you have seen and which I have given earlier, like iron, kettle, oven, toaster and all these. A kettle uses both copper and nichrome wires. Copper has low resistance while nichrome has high resistance. Here, if you have observed, a kettle uses both copper wire and nichrome wire. A kettle uses two different types of wires, that is copper and nichrome wire. Copper has low resistance whereas nichrome has high resistance. So here you have to decide which wire can be used for the heating element and which is used for external wiring. So if you have observed, not only in kettle, most of the electrical appliances, copper wire is used for external wiring since it has low resistance and produces less heat, and since nichrome has high resistance, it is used for heating element. So that is what here given clearly. Use copper wire for the external wire as it has low resistance and produces less heat, and nichrome wire is used for the heating element as it has high resistance and produces lot of heat. So here in this slide you can see the coil, which is the heating element. Getting into its details, the heating element concealed inside a ceramic cooktop. This is one continuous element beginning at the blue dot and curving around in a maze shape until it reaches the red dot. As I said, this is in a coil shape, and if you observe closely, it starts with the blue dot and continues like a maze and ends at a red dot. So here there's no point in this element being any other shape or size. If you observe, most of the electrical appliances which are running on the heating effect are mostly in this curved shape, since it has to concentrate heat precisely underneath a cooking pan. So here why they are mostly designed in a circular shape is they have to concentrate most amount of heat precisely, means very concentratedly, in this coil, in this heating element, and this is the most effective way to achieve the heat. So here in this also you can see that the heating element is in coil shape, and this heating element is from the water heater. Another one, this is the toaster. You can see that the heating element gets heated. It has turned to red hot due to the heating effect of electric current. You have seen that the electrical appliances like electric iron, toaster, heater, water immersion heater, then kettle, induction coil, all these are having heating element in them. So this heating element is the main core part of the electrical appliances, and it should have certain properties to achieve high heating effect in them. Let's see what are those properties. The first one is high melting point. Next, high resistivity, high tensile strength, shouldn't get oxidized at high temperature, shouldn't expand at high temperature. Let's go back to the first point, that is high melting point. So here, why the heating element should have high melting point is, here this heating element in this electrical appliance gets heated up to a large high temperature. So when it is getting heated up to a high temperature, if it gets melted, then the coil breaks. Then large amount of heat cannot be concentrated. So when the coil breaks, then amount of heat gets dissipated there. Due to this reason, the heating element should have high melting point. Then next property, high resistivity. Why the heating element should have high resistivities. The larger the resistance, the larger is the amount of heat it can store. So it should have high resistivity. The next, high tensile strength. Now let's see what is this tensile strength. Tensile strength means the strength of an element or the strength of a metallic wire to be stretched is known as its tensile strength. That is, whenever a wire or an element is being stretched, if it stretches without breaking, then it is known as its tensile strength. Here, the heating element which is chosen for this electrical appliance should have high tensile strength, because this heating element should be molded into a coil. So it should have high tensile strength. The next property is it shouldn't get oxidized at high temperature. Since this heating coil is getting heated up to a high temperature, it should not combine with, or it should not react with oxygen in the air. So it shouldn't get oxidized. The next property, it should not expand at high temperature, or else the length of the coil increases. You know that the electrical appliance like electric iron, which is used to iron the clothes or to press the clothes, a kettle used to heat the liquids, a toaster used to toast a bread, are all these appliances which function or which works on the heating effect of electric current. So do you think that the heating effect of electric current is limited only to heat? No, it has its other application. Let's see what it is. That is, the electric heating is also used to produce light. Example, electric bulb. So here it means that the heating effect is not only limited to heating, it is also used to produce light. That is, in a bulb, the filament retains as much of heat generated as is possible so that it gets very hot and emit light. So here, how does the heating effect is producing light is, for example, when you take an electric bulb, it contains filament. This filament retains, means it can store as much of heat generated as is possible so that it gets very hot and emits light. So this filament retains, it stores or it regains the amount of heat which is generated, which is produced in the circuit, and it slowly gets heated up and then emits light. So here this filament should not melt at such high temperature. So the first requirement for choosing heating element, that is, should have high temperature or it should have high melting point. A strong metal such as tungsten with high melting point 3380 degrees centigrade is used for making bulb filament. Since this filament should have high melting point, a strong metal such as tungsten is chosen for making these filaments. It has the melting point 3380 degrees centigrade. Due to its high melting point, it is used to get heated up to a high temperature and can emit light. Okay. The filament should be thermally isolated using insulating support, which means that the filament which is chosen in a bulb should be thermally isolated, means should be isolated means separated thermally using the insulating support. So to do this, the bulbs are usually filled with chemically inactive nitrogen and argon gases to prolong the life of the filament. So here when this tungsten metal or tungsten filament or any filament which is present in the bulb, it should be isolated. So to do this or to achieve this, the bulb is filled with chemically inactive gases like nitrogen and argon gases so that it doesn't react with tungsten. In this way, it helps to prolong the life of the filament. Most of the power consumed by the filament appears as heat, but a small part of it is in the form of light radiated. So here, when it is not reacting with these gases which are present in the bulb, the large amount of heat gets stored by the filament, and as long as it is restoring, most of the power is consumed by the filament and it appears as heat. Due to high temperature, it gets heated up, and a small part of heat is converted in the form of light. That light is radiated, means it is given or emitted in the form of light. So here is the example bulb, which contains a filament, which is a thin wire, tungsten wire, which is producing heat and light. In a light bulb, the heated filament, which is also a resistance wire, becomes so hot that light is also emitted. So here this tungsten is a metal which is also a resistant wire, means it has its resistance, but its resistance is too so high that it becomes hot and emits light. Now let's try to understand how this amount of heat which is released in a circuit can be measured. Consider that a charge Q coulombs passes through a point A, moves to a point B in a time interval t seconds. So imagine that charge of Q coulombs passing from point A to point B in a time interval of t seconds. Then let V be the potential difference between these 2 points. Then work done by the electric field in time t is given by W is equal to Q into V. So imagine that in a circuit, a charge of Q coulombs is moving from point A to point B. This charge of Q coulombs is moving within a time of t seconds. Then work done by the electric field, because here this movement is happening or this movement is possible because of the potential difference V. So here the work done by the electric field due to this potential difference V is given by W is equal to Q into V, where Q is the charge of Q coulombs and V is the potential difference between these 2 points. So here this work, which is equal to QV, is equal to the energy lost by the charge while passing through the conductor, because we know that when electrical charge is flowing, heat is also produced. It is inevitable. So this same amount of heat is also produced in the conductor. So the source must supply energy equal to VQ in time t. So here the amount of work done is converted into heat. So here the power input to the circuit by the source is electrical energy consumed per unit time. So we can say that the amount of electrical energy consumed per unit time is its power. So we can say that the amount of energy which is consumed in an unit time is being converted to heat energy. So the amount of power in the circuit is equal to the work done per unit time. So P is equal to W by T, and we know that W is equal to V into Q by T, and Q by T is equal to I from Ohm's law. So P can be written as VQ by T or V into I. But from Ohm's law, we know that V is equal to IR. So if you replace V with IR, then P is equal to I square R. Hence P is equal to I square R or V square by R or V into I. So from this we can say that the energy supplied to the circuit by the source in time t is P into T, and this is the energy that is getting dissipated in the resistor as heat. So this much amount of heat, that is P into T, is the amount of heat which is getting converted. Hence we can say that H is equal to Vi into T, because we know that P is equal to V into I. Then H is equal to Vi into T, or else we know that P is equal to I square R, and hence H is equal to I square R into T, because we know that H is the equal to P into T, that is power into time. And we all have the formulas, that is P is equal to I square R. Hence, H is equal to I square RT. Or if we take P is equal to V into I, then H is equal to V into I into T. Okay. Then let's see the units of electrical power. The units of SI units of electrical power is watt. That is 1 watt can be defined as the power consumed by an electrical appliance which when operated at a potential difference of 1 volt carries a current of 1 ampere. So here what is 1 watt means 1 watt can be defined as the power consumed by an electrical appliance at a potential difference of 1 volt carrying a current of 1 ampere. And the other unit of electrical power is kilowatt. This is a bigger unit which is used for commercial purpose, and 1 kilowatt is equal to 1000 watts, or it is equal to 1000 joules per second. We know that H is equal to I square RT. This is known as Joule's law of heating. This law implies that heat produced in a resistor is directly proportional to the square of current. Since H is equal to I square RT, it is directly proportional to square of the current, the resistance for a given current, and to the time for which the current flows through the resistor. So, the Joule's law of heating H is directly proportional to three values, that is first thing square of the current, second one resistance for a given current, and third one is time for which the current flows through the resistor. Then relation between kilowatt hour and joule. What is this? So here when we are measuring that electric current is passed in a circuit and it is getting converted into certain amount of heat. So here the consumption of electricity, that is the consumption of electric energy, is measured in kilowatt hour. That's what you have seen earlier. Now what are the units of electrical energy is kilowatt hour. Watt hour or kilowatt hour, which is used for commercial purpose. And what it is equal to, 1 kilowatt hour is equal to 1000 watts into 1 hour. You know that 1 kilowatt is equal to 1000 watts. And here 1 kilowatt hour is units of electric energy. So 1 kilowatt hour is equal to 1000 watts into 1 hour. And we know that 1 hour is equal to 3600 seconds. So it can be converted as 3.6 into 10 to the power of 6 watt seconds, or it is equal to 3.6 into 10 to the power of 6 joules. Now let's see the rating of electrical appliances. That is power voltage rating, means the usage of power or the voltage by the electrical appliance. The power rating of an electrical appliance tells us the rate at which the electrical energy is consumed by the appliance. So here what does this means is the power rating of electrical appliance, any electrical appliance which you are using, its power or its rate can be known by the electrical energy that is consumed by it. So the rate at which the electrical energy is consumed by the appliance is its power rating. If the power P and the voltage V at which the appliance works is known, then by using the relation P is equal to V into I, we can calculate the current drawn by the electrical appliance. We know that P is equal to V into I. If we know at which voltage the appliance is working, then we can calculate the amount of current drawn by the electrical appliance. So using these formulas, in the next class we are going to solve some problems related to power. Okay, thank you.